So quantum mechanics is the theory of all the stuff in the universe. Everything you see, hear, feel, touch, or everything you're made of is all described by quantum mechanics as far as we know. But we've only really known about quantum mechanics for the last century or so, and it took scientists several decades to kind of sneak up on the theory because it was such a radical change from the other theories that they were beginning to feel they really understood. However, we can talk about quantum mechanics with a very simple experiment, the two-slit experiment, which Feynman said contained the heart of quantum mechanics. And he reckoned basically all of the mystery of quantum mechanics could be described within the shape of the two-slit experiment. So the basic idea of the two-slit experiment is very simple. You just take a sheet and you put two slits in it. You're going to throw something at that sheet from one side, and on the other side you're going to detect it on a detector. And why might you do such a thing? Well, you're trying to find out whether these things, these green things here, are a wave or a particle. So what's a particle? A particle is something that has a particular position and a particular velocity, and it might have some properties like mass or charge or other things like that. And a wave is something that's spread out and it's oscillating, and so it can make ripples, it can have constructive and destructive interference. And there doesn't seem to be any particular confusion about something like a pebble, which people realize that's something like a particle. And there's no confusion about obviously a water wave, which is clearly a wave. And circa 1800, everyone would have said the same thing about light. It's obviously a particle, they'd say, because that's what Newton said, and everything that Newton said turned out to be right. But it turns out that when Newton wrote that in his treatise Optics about 100 years previous, the reason he'd done that was not because he'd had any proof that light was a particle, but just that he felt that light was a particle. And Thomas Young developed an experiment that would show exactly whether something was a wave or a particle, and that was the two-slit experiment, also known as Young's double-slit experiment. So the idea here is fairly simple. If you send things through a pair of slits, then if they're particles, if they go through one slit, they'll make a big fuzzy blob. It's a big fuzzy blob, and maybe we can't resolve the individual clicks of the particles, but if we send a lot of them through, we'll get a big fuzzy blob. And if we send them through the other slit, we'll also get another big fuzzy blob. And if the fuzz of the two kinds of blob are sufficiently wide, what we'll get is a kind of joint fuzzy blob. And that's all we'll see. That's if they're overlapping. However, supposing it's actually a wave, then if you have a wave going through two slits, then the oscillations of the wave are going to be going in and out of phase. And as you move across this screen, across here in this direction, the amount that they're in and out of phase is going to change, and so they're going to be giving constructive and destructive interference. Now remember, constructive interference, if you have one wave doing this, and you have another wave doing exactly the same thing, when you add those up together, you get a larger wave. Whereas if these are out of phase, then what you get is basically nothing. And so the net result is that if you have something going through two slits and it's a wave, what you're going to see are regions of bright and dark bands. And the bright bands will be where you have constructive interference, and the dark bands will be where you have destructive interference. The particular positioning of these constructive interference fringes depends a lot on the spacing between these two slits, and indeed some of the shape of it depends on the size of these slits. And so you don't necessarily see those fringes very clearly when you put it through two slits unless you make the spacing and the sizes of these slits appropriate to the wavelength of that wave. So if the natural wavelength of the wave that you're putting through there matches that spacing, then you're going to see something significant over on the screen. So Young used sunlight as his source, and he put it through a little pinhole so we get a nice single point source of sunlight, and then he put it through two other pinholes, and he saw his interference fringes, and from the placement of those he figured out that the wavelength of the red light was around about a micron, and the wavelength of the blue light was around about half that. And the other main thing he showed was that light was clearly a wave, because you can't possibly get interference fringes if you don't have a wave. You can't get two particles adding together to give you nothing, or two particles adding together to give you the equivalent of four particles. It has to be a wave if you're going to have interference. And so we went and published this and showed, yes, light is a wave, I've shown it. And this, of course, made people very angry. And so corpuscular theorists attacked him in the Edinburgh Review, and eventually he was sufficiently undermined that he went back and focused on medicine for a while. In the years to come after that, Fresnel wrote a thesis about wave properties of light, and Poisson tried to prove him wrong by saying, well, obviously if light's a wave, then if you have a perfectly round object, then what you should have in the middle of the shadow is a bright spot, because all the light going around the edges of your blockage should all constructively interfere there, and you get a bright spot. Now, people originally took Poisson's suggestion as a disproof of the wave theory of light because no one had ever seen bright spots in the middle of shadows before. But in order to expect that bright spot, you have to have your surface smooth on the scale of the wavelength of the wave. And given that the wavelength of the wave was supposed to be around a micron, it took them a while to make a ball that round. And when they did, of course, what they saw was this bright spot, now called Poisson's spot. And so our final conclusion was that light is certainly a wave.